The universe is expanding faster than physics allows. Those are not my words. Those are the words of Adam Riess, a Nobel Prize-winning physicist at Johns Hopkins University, who has spent the last decade measuring how fast the cosmos is flying apart. His team's number, drawn from supernovae in the local universe, disagrees with the number drawn from the cosmic microwave background by 7%. That gap should not exist, and it has not closed in 12 years. The Hubble constant is one number. It tells you how fast a piece of the universe 1 megaparsec away is moving from us. 1 megaparsec is roughly 3.25 million light-years. The number itself is written h0, and the units are kilometers per second per megaparsec. For 100 years, measuring this number has been the central project of cosmology. Edwin Hubble drew his first version of the curve in 1929 on photographic plates with a pen. The curve had a slope. The slope was the constant. He got it wrong by a factor of 7, but the principle was right. Galaxies recede. The further they are, the faster they recede. The constant tells you how fast. In the standard cosmological model, the one we have spent the last 60 years building, called lambda CDM, there is exactly one Hubble constant. It is set by the geometry of the early universe, the density of matter, and the density of dark energy. It also depends on the speed at which sound waves moved through the plasma in the first 380,000 years, before atoms even formed. Plug the parameters in. The model gives you one number, not a range. 1. 2 teams measure it. Both teams are extremely good at what they do. One team measures it locally by climbing a ladder of distances, rung by rung, from nearby stars to far galaxies. The other team measures it from the leftover heat of the Big Bang, the cosmic microwave background, which fills every cubic meter of space at a temperature of 2.7 Kelvin. The local team is the SHOES collaboration. Supernovae and H0 for the equation of state of dark energy. Adam Riess leads it. They use the Hubble Space Telescope, and as of 2023, the James Webb Space Telescope, to identify Cepheid variable stars in galaxies near enough that they can also see Type 1a supernovae. Cepheids pulse in a way that gives away their true brightness. Type 1a supernovae always explode at almost exactly the same true brightness. 2 standard candles, calibrated against each other, calibrated against parallax measurements at home. A ladder. 12,000 cited papers, a 7% precision target. They published their flagship value in 2022 in the astrophysical journal Letters. H0 equals 73.04 plus or minus 1.04 kilometers per second per megaparsec. The other team is the Planck collaboration. Nobody leads Planck the way Riess leads SHOES. It is European Space Agency run, with thousands of authors. Their flagship value comes from the cosmic microwave background, which the Planck spacecraft mapped from a Lagrange point 1 million miles from Earth between 2009 and 2013. The CMB is the universe's earliest photograph. It gives you the geometry, the densities, the sound horizon, every parameter the standard model needs. Plug them all in. The model spits out H0. Their published value, in the 2020 legacy paper, is 67.4 plus or minus 0.5 kilometers per second per megaparsec. 73.04 from one team, 67.4 from the other. The error bars do not overlap and have not overlapped for 12 years. Both teams have spent that decade hunting for the systematic that would close the gap, and neither team has found it. Each side has run the same data through alternative pipelines, swapped in different anchor calibrations, and rechecked the supernova standardization against independent samples. The numbers move by fractions of 1%. The gap remains. That is the Hubble tension. It is the most precisely measured disagreement in cosmology and one of the longest-lived structural anomalies in modern physics. It has outlasted 4 major cosmological surveys, 3 new space telescopes, and roughly 500 peer-reviewed papers attempting to explain it. 5 sigma is the threshold particle physicists use for discovery. It means the probability of seeing a result this extreme by chance, given the model is correct, is about 1 in 3.5 million. The Higgs boson was announced at 5 sigma. The first gravitational wave detection was announced at 5.1. A 5 sigma deviation from a theoretical prediction is the level at which the field stops debating whether the prediction is wrong. The latest tension calculations between Shoes and Planck land between 4.4 and 5.4 sigma, depending on which systematic uncertainty model you use. That is not a measurement disagreement. That is a structural break. To put it another way, if both measurements are correct, the standard model of cosmology is wrong. Not slightly wrong. The standard model assumes 1 Hubble constant. 2 values that disagree at 5 sigma cannot both come from the same model. This is what Riess himself said in a 2023 lecture on camera before an audience of physicists. His exact words were, "We've checked everything we can think to check." What he meant was concrete. The Shoes team had spent over a decade rerunning every potential systematic. Cepheid metallicity bias, dust extinction, crowding effects in nearby galaxies where multiple stars overlap on a single Hubble pixel. Anchor calibration to the parallax from the Gaia mission. Each one was studied, modeled, and ruled out as the cause of the gap. None of them shifts the Shoes number toward Planck by anywhere near 4 sigma. Riess himself, the man whose Nobel Prize is for measuring the universe's accelerating expansion, has run his own measurement against itself for 10 years and cannot find the error. The Planck team has done the same on their side. Anthony Challoner, George F. Stathu's collaborator at Cambridge, has run the analysis multiple times against the same data with different priors. Each version returns 67 to 68. The answer the CMB gives is robust. 2 robust answers. They cannot both be right. And the gap has been there since 2014, when the Shoes preliminary value first crossed 3 sigma over the Planck value. 12 years and 4 sigma later, both teams are still standing on their numbers. That is the structural part. The tension is not a measurement settling down toward truth as instruments improve. It has hardened. It has been there long enough that an entire literature has formed around explaining it. In the meantime, 10 other measurement methods have weighed in. Time delay gravitational lensing, megamaser distances, standard sirens from gravitational waves, tip of the red giant branch distances, calibrated by Wendy Friedman at the Carnegie Observatories. Type 2 supernovae, spectrally modeled. Tully-Fisher calibrated rotation curves. Fast radio burst dispersion measures. Galaxy cluster scaling relations. Each one returns a number. The numbers do not all agree. Some land near 73, the Shoes value. Some land near 70. Some land near 67, the Planck value. Some land below 67. The pattern is not random, and the pattern is not converging. Different methods return different numbers, and the differences cluster. This is why the field has stopped calling it a tension and started calling it a crisis. Start at the bottom of the ladder. The local universe team needs to know the true distance to a few nearby anchor galaxies. They use parallax, the small wobble of nearby stars against the background as the Earth moves around the Sun. The Earth's orbital diameter is the baseline. 6 months apart, 2 photographs of the same star, and the angular shift gives the distance directly. Gaia, an ESA mission launched in 2013, has now measured parallax for over 1 billion stars. Anchor distances inside the Milky Way are nailed down to 0.5%. There is no give in the bottom rung. The geometry is just trigonometry, the same way a surveyor measures a building from two ends of a street. Above parallax sit the Cepheid variable stars. A Cepheid pulses on a specific timescale that depends on its true brightness. Time the pulses, and you know how bright the star really is. Compare to how bright it looks. The ratio gives you the distance. Henrietta Leavitt worked out the period luminosity relation in 1908, before quantum mechanics existed. Modern Cepheid measurements using Hubble's Wide Field Camera 3 are precise to under 2% per galaxy. Above Cepheids sit Type 1a supernovae. A Type 1a is a white dwarf that has accreted enough mass to ignite carbon fusion runaway. The peak luminosity is set by the Chandrasekhar limit, a number from quantum statistics. Every Type 1a peaks at almost exactly the same true brightness. They are visible across the observable universe. Cepheid distance measured in nearby galaxies. Type 1a peak in those same galaxies, calibrated against the Cepheid distance. Then Type 1a peaks observed in much more distant galaxies, where the Cepheids are no longer resolvable. The distance ladder, each rung calibrated against the one below. This is the shoes method. 40 rungs of cross-calibration, each one squeezed for systematic error. The 2022 result is the cleanest version of this measurement that has ever existed. Now the second method, the cosmic microwave background. The CMB is the photograph of the universe at age 380,000 years, when the plasma cooled enough for atoms to form and photons to travel freely. The pattern of temperature fluctuations on the CMB sky encodes the geometry of the early universe. Flat, nearly flat. What density of matter? What density of dark energy? Planck mapped these fluctuations to a sub-microkelvin precision over 4 years. Run the standard model forward from those parameters. It tells you what the Hubble constant should be today, 67.4. The error bar is half a kilometer per second per megaparsec. The CMB does not measure the local universe. It measures the conditions of the early universe and propagates them forward. If the standard model is correct, the two values should match. They do not match, and the gap is not narrowing. So independent measurements have stepped in. Take the Megamaser cosmology project. Megamasers are water vapor clouds in the accretion disks of supermassive black holes. They emit at a precise radio frequency. The geometry of the orbit lets you measure the distance to the host galaxy directly. No ladder, no calibration to a brighter object. The MCP has measured 9 Megamaser galaxies to date. Their combined Hubble constant, about 73, consistent with shoes. Or take time delay cosmography. When a distant quasar's light passes through a foreground galaxy, gravity bends it. If the foreground geometry produces multiple images of the same quasar, each image takes a slightly different path. The light arrives delayed. Time the delay, model the geometry, recover the distance. The H0 LICAO and TD Cosmo collaborations have done this for 7 gravitationally lensed quasars. Their combined value, 64.8 to 66.6 kilometers per second per megaparsec, consistent with Planck. Or take gravitational wave standard sirens. When LIGO and its partners detected the merger of 2 neutron stars in 2017, the event GW170817, they recorded both the gravitational wave and the optical afterglow from the same source. The gravitational wave signal lets you measure the distance directly, with no ladder. From that single event, plus a few more recent ones, the standard siren H0 measurement is roughly 72.5, pulled towards shoes. Or take fast radio bursts, millisecond duration radio pulses from distant galaxies. The dispersion of the pulse as it travels through intergalactic plasma encodes the column density it crossed. McQuart and collaborators used this to measure H0 in 2022. They got 73, with very wide error bars. Shoes side. Or take Type 2 supernovae, spectrally modeled. They are not standard candles in the way Type 1As are, but the expanding photosphere method gives a ladder-free distance. Recent results sit near 70. Or take the Tully-Fisher relation, calibrated against galaxy rotation curves. A 2024 paper by Bubel and collaborators returned 76.3, the highest value in the literature. Pulled hard towards shoes and beyond. Add it up. Methods that calibrate through the local distance ladder cluster near 73. Methods that measure through the CMB or through baryon acoustic oscillations cluster near 67 to 68. Methods that bypass both gravitational lensing, megamasers, gravitational waves, FRBs, split. Some go local, some go cosmological. The mid-value methods are vanishingly rare. This is not a single discrepancy between two teams. It is a clustering pattern, and the clusters do not overlap. The Cepheid distance ladder is not the only ladder in town. There is a second ladder called TRGB, the tip of the red giant branch. When a sun-like star runs out of hydrogen in its core, it swells into a red giant. The red giant phase ends in a flash when the helium in the core ignites. The brightness of stars at this turning point, the tip of the red giant branch, is set by stellar physics that does not depend on metallicity in the way Cepheid pulsation does. The TRGB tip is, in principle, a cleaner standard candle. Wendy Friedman has been running the TRGB-based Hubble constant measurement for over 15 years through a program called the Carnegie-Chicago Hubble Program, CCHP. Her flagship 2024 result puts H0 near 70, closer to Planck, lower than shoes by about 3. 3 is a lot when both teams claim sub-1 statistical errors. The Cepheid camp says the TRGB calibration is contaminated by foreground extinction and selection effects in the host galaxies. The TRGB camp says the Cepheid period luminosity relation has metallicity-dependent systematics that have not been adequately modeled. Metallicity matters because Cepheids in metal-rich galaxies pulse at slightly different periods than Cepheids in metal-poor galaxies, even at the same true brightness. Get the metal correction wrong, the shoes team's number drifts. Get the foreground dust correction wrong, the CCHP team's number drifts. Each side has a story for why the other side is wrong, and each story is technical enough that the dispute will not be settled by one observation. Friedman has gone on record stating plainly that Cepheid-based calibrations may harbor subtle systematics. The convergence of TRGB, megamaser, and gravitational lensing measurements, she argues, suggests the true H0 is closer to 70 than to 73. Riess and the shoes team disagree. Their position is that Cepheids, calibrated against Gaia parallax and cross-checked with JWST, are now the most rigorous standard candle in the local universe. Both positions are defensible. Both positions have collaborations behind them. Both positions cannot be right. This is the first contradiction in the literature. Two teams, two ladders, two values, both internally consistent, both backed by collaborations with hundreds of authors, both pointing at different conclusions about whether the standard model is in trouble. Then James Webb arrived. The Webb telescope's near-infrared resolution is roughly twice as good as Hubble's, in the wavelengths where Cepheids are brightest. If the Cepheid problem was crowding, multiple stars overlapping on a single Hubble pixel and corrupting the brightness measurement, JWST should resolve it. In 2023 and 2024, Riess and the shoes team re-imaged a subset of their nearby Cepheids with JWST in a paper they called Crowded No More. Their result? H0 of 73.0 plus or minus 1.0. Identical to the Hubble-only shoes value. Crowding, the Cepheid camp announced, is not the cause. But the JWST sample was small, fewer than 50 Cepheids across a handful of host galaxies, and several independent reanalyses pushed back almost immediately. The Mortzel and Gubar paper, also in 2024, argued that the JWST sample carries a different bias. The anchor galaxy selection introduced a systematic that mostly cancels with the crowding effect by accident and produces a high value through a different route. George F. Stathiou's group at Cambridge weighed in late in 2024. His paper, on archive preprint number 2412.07840, took the JWST sample, separated the anchor galaxies into individual fits rather than a global fit, and recovered H0 of 70.3 plus or minus 2.1, 3 sigma below the SHU's headline. He concluded that the Cepheid period luminosity relation differs across anchor galaxies in a way the global SHU's analysis treats as a single number. If you let the anchors disagree, the answer drifts toward the TRGB and Planck cluster. This is the second contradiction. Did JWST settle the Cepheid systematics question, as the SHU's team argues? Or does the JWST sample carry its own anchor population bias that suppresses the apparent disagreement, as F. Stathiou and others argue? The papers are public. The methods are public. The answer is not. Both contradictions remain open as of this filming. Step back from the ladders. When two extremely careful, extremely well-checked measurements disagree at 5 sigma, 3 things can be true. The first measurement is wrong, the second measurement is wrong, or the model that connects them is wrong. The systematic error explanations on each side have been pursued for over a decade. Crowding bias, metallicity, dust extinction, anchor selection, supernova standardization. The SHU's team has run controls for every one of these, and the JWST cross-check eliminated the most plausible candidate. The Planck team has run independent reanalysis with different priors and recovered the same CMB value to within a fraction of their stated error. Neither systematic story has produced a 4 sigma shift. That leaves the model. The leading new physics resolutions cluster into a few families. First, early dark energy. A team led by Mark Kamionkowski at Johns Hopkins and Vivian Poulin in Montpellier has proposed something elegant. A transient dark energy component, present briefly before recombination at age 380,000 years, would have shrunk the sound horizon. The sound horizon is the standard yardstick the CMB analysis uses to convert geometry into H0. A smaller sound horizon at recombination means a faster local expansion today, computed from the same CMB data. Their models can lift the Planck-inferred H0 from 67 towards 71 or 72, partially closing the gap. The trade-off is that early dark energy must come and go in a narrow window in cosmic history. It also tightens constraints on large-scale structure that some authors say push back. Second, modified gravity at cosmological scales. Theories like F of T gravity or interacting dark energy let the expansion history accelerate locally without violating CMB observations. They also have free parameters, and the data so far does not rule them out, but does not select between them either. Third, sound horizon shifts from non-standard recombination physics. If recombination happens slightly differently than the standard model assumes, through varying primordial baryon abundance, or through additional photon-baryon coupling, the inferred sound horizon shifts, and the local universe implied H0 changes. Knox and Millea published a careful classification of these scenarios in 2020. As of the 2024 literature, none has emerged as the consensus answer. Fourth, dark energy that is not constant. The DESI collaboration's 2024 baryon acoustic oscillation result drew on over 5,000 galaxy redshifts. It hinted that the dark energy density may be evolving with time, in tension with the cosmological constant assumed by the Planck analysis. If dark energy is evolving, the Planck-inferred H0 must be recomputed with a different model for late-time expansion. Early DESI results pushed the Planck value upward by about 0.5 km per second per megaparsec. Not enough to close the shoes gap, but enough to register. The 2025 DESI Year 3 update is expected to either confirm or rule out evolving dark energy at higher significance. What this list has in common: every entry is a modification to the model, not to the measurements. The measurements have stopped being the suspect. The standard model itself is. This is what makes the Hubble tension different from past discrepancies in cosmology. The Andromeda distance was wrong because of a Cepheid calibration error in the 1950s, and Walter Baade fixed it. The age of the universe debate in the 1990s was resolved when better instruments returned better numbers. The Hubble tension has not closed with better instruments. Hubble, JWST, Planck, Atacama Cosmology Telescope, the South Pole Telescope, Euclid, DESI, Roman, LIGO. Every new instrument has come online, and the gap has held. 5 Sigma, 12 years. Multiple independent methods clustering around 2 different answers. A leading candidate Nobel laureate publicly stating he does not know what is causing it. That is the structural break. The next decade decides which family of explanations survives. The Vera Rubin Observatory comes online in 2025 and 2026 with a survey that will calibrate Type 1a supernovae against thousands of host galaxies a night. The Roman Space Telescope launches by 2027, and its wide-field instrument will measure the dark energy equation of state to better than 1%. JWST will continue to extend the Cepheid distance ladder. Euclid, already in space, is mapping the matter distribution out to redshift 2. Each of these missions will return its own version of H0, and the cluster of values it produces will tell us which side, if any, was correct. If the shoes value holds, and Vera Rubin agrees, the standard model is wrong, and one of the new physics resolutions becomes a candidate for replacing it. If the Planck value holds, and the local universe values converge downward towards 70, then the systematic was hiding in the Cepheid ladder all along, and lambda CDM survives. Either outcome is, on the scale of cosmology, an event. The wrong but useful map we drew of the universe gets redrawn. The next version, whoever draws it, has a different shape. If new physics is required to close the gap between Adam Riess and the cosmic microwave background, the universe we have been describing for 60 years is, in an important sense, the wrong universe. The right one is going to be stranger and more beautiful than anything we've drawn so far. Thanks for watching, and I'll see you in the next one.